So I want to begin by quickly recapitulating some of the things that I said last time. For which, so let me begin by setting up a little notation which is sometimes useful. Suppose X is a Banach space. And suppose E is it can just be a subset. But okay, let me just say, I can even be just a set, some subset of the dual space, the space of continuous linear functionals. Okay. Then one defines by this one means the smallest topology with respect to which everything in S is continuous. So what that means is X alpha converges to X if and only if X alpha converges to Fx for all F in S. Okay. This is the way you define the weak topology, weak star topology, and so on, for appropriate choices of the set S. Now, I'm being silly by saying you take a set S. In fact, one can see that if you take this is really the same as if things in S are continuous, then linear combination of those things are going to be continuous. Right? So you might as well assume that the set inducing the topology is a vector space, vector subspace of this X star. And in general, okay, so here's a little proposition, lemma, whatever, fact, which you will find, for example, it is not hard to prove. You will find this fact in that those notes of Stratila and Jito, the first few pages that I gave you on, what is the thing? The first thing that I gave you. Okay, so it is not hard to see that if what should I call it? If B is a norm-bounded subset of X. So, for example, let me say, or is a equivalently a bounded set in X. If you have a norm-bounded subset of X, then I am saying that sigma xb, this topology with and no, I don't want B, sigma x, okay, sorry, no, I don't mean, and if, let me say, if E contained in X star is a vector space, I will assume there is a vector space now, then I want to say that sigma x E, the subspace topology, I'll say, and sigma x E closure on E are the same, give the same topology on E. This is the kind of argument that we discussed in the, on on B, sorry. See, these are topologies on X. So if I take B with the subspace topology coming from either E or E closure, then I get the same topology. Okay, so this is proved by exactly the same motion that we went through during the tutorials on Monday. Okay, okay. So or equivalently, what this says is that so what this says is that i.e. f x alpha converges to f x. When I say this, implicitly I am assuming that x alpha is the net in X. This holds for all f in some set S, if and only if. The same thing holds for all f in span S, if and only if for all f in spanless closure. Okay, this is really the upshot of what I said before. For x alpha S coming from some non-bounded set. If you have a net which is uniformly non-bounded, to say that you have convergence against everything in S is the same as saying you have convergence against everything in the norm closure of the span of S. Okay, and so allow me 2 more minutes of this generality before I get to B of H. Okay, and the next remark I want to make is that if okay, I'll say if E closure equals F is separable, so if the subspace that gives the topology is separable, or equivalently I look at a set S which is countable, and I look at the corresponding sigma xs on bounded sets. Okay, then the statement is then the subspace topology on B again and B bounded for bounded B is metrizable, i.e. In fact, with respect to I'll even tell you what the metric is. D of xy. So I take some. What does this mean? This means that you have some set Fn, which is dense in E closure in F.
Maybe we should tell how to define a topology by just assigning convergent nets. Because the idea of convergence of net already assumes there is a kind of topology, and there's a bit of danger also whether topology is unique or not.
No. Okay, so there is this thing that one has to say that if you given any subset E of x star, one can talk of the smallest topology with respect to which smallest vector space topology with respect to which all those things are continuous. So I think you would have seen all of this in weak topology.
Neighborhood base also, rather than nets.
No, I don't want to go. I am trying to minimize points at topology. So that is why I want to just use the language of nets, and it is everything that you expect to happen will happen. So this you can say is sum over n absolute fn x minus fn y, or just fn of x minus y. I have to normalize. If I do this, then this will be a convergent sum. And to say that this is 0, to say that dxn y is 0, is exactly the dx alpha 0 says that fn x alpha converges fn y for every n. That means exactly the topology is sigma x f restricted to the bounded set B. Okay, so there is just some silly topology that I want to get out of the way before we get on to using these facts. Okay. Now, of course, we will be interested in using in the case where x equals B of h. And f e for me, actually unfortunate notation, e for me will be so sigma x e for me will be the weak operator topology. Okay. That is, E is things of the form an element of E looks like f of an x equal to summation 1 to n x psi I eta I. So these are the weakly continuous. Those are the linear functionals on B of h that I want to be continuous. So if I do this, then will be okay. And then let me let me change notation. Let me call this as f. There is a reason for this. So I will write f for all functionals which look like this. For finite, f for finite. For all finite sums of this kind. Okay. And so by what we've seen, the topology sigma xf on bounded sets is the same as sigma of xf closure. This f is clearly an element of B of h star. Right? For every f in of this form, if we take finitely vectors, when you vectors e and eta, x going to xi eta is continuous. Right? So with respect to the operator norm on B of h, these are continuous functionals, and so I am interested in this topology, right? And so now this will be called, I mumbled some words yesterday, this will be the so-called sigma weak topology. I will have more to say about this before too long. Okay, so what is going on here? So let me back up. So I'll tell you, I'll get to where I'll use all this stuff. So you have seen in Patho's course, so you're talking about C-star algebras. There's an abstract definition which is concrete. he defined a C-star algebra abstractly as some Banach algebra equipped with as a star algebra which satisfies that C-star identity. Right? That is an abstract definition of a C-star algebra. By concrete C-star algebra, I will mean a norm-closed subalgebra, star subalgebra of B of H. Right? And there is a theorem, the so-called Gelfand-Naimark theorem, which will tell you that any abstract C-star algebra is isomorphic to a concrete C-star algebra. Similarly, in von Neumann algebras, there is an abstract definition and a concrete definition. The abstract definition is, so let me just say, an abstract von Neumann algebra is M is first a C-star algebra such that, and 2, there exists M lower star, i.e. M as a Banach space is the dual space of some other norm space, in fact a Banach space. So a C-star algebra which admits a pre-dual in this sense is an abstract von Neumann algebra. Okay? And on the other hand, a concrete von Neumann algebra is an M sitting inside a B of H such that it's a star subalgebra satisfying the conditions of the double commutator theorem that I mentioned last time. Or the same as saying it is SOT closed or WOT closed or whatever. Okay. So maybe I should have said something. No, not yet. I'll come to that. I guess I should have said something else when I was saying these earlier things about the sigma xf and so on. So I define the sigma weak topology as the topology, as this topology where it is a closure, sigma x B of H F closure. Okay, so I'm jumping back and forth because I didn't follow the order correctly. Okay, so let me kind of tie the end of this string. So here also there is a Gelfand-Naimark theorem, which will say that any abstract von Neumann algebra is isomorphic to a concrete von Neumann algebra. Okay, which is something that we will see as we go along. Okay, and in all this, what is okay? If you take this, okay, let me give some. Okay. So examples of abstract one. An example of a concrete von Neumann algebra is easy to get. You take B of H and you take any star closed SOD closed subalgebra, that is a von Neumann algebra. Right? Unital. Okay, but at the abstract level, for example, you have L infinity. Let me call it omega mu. I take some measure space L infinity and look at the space of essentially bounded measurable functions with the essential supremum norm. then you can see that it is a C-star algebra with the soup norm, and it has a pre-dual, namely L1. Okay. Second, then, and this is a fact that I will spend a little time talking about. In fact, B of H itself is an abstract polynomial. It is clear that it is a C-star algebra. So I just have to tell you what its pre-dual is. Right? So it is true that in fact what I called with B of H star is what I call F closure, where F was all those finite linear combinations of those inner product functionals. Okay? You remember this F that I wrote down before? Linear functionals on B of H that look like this, they are a subspace of B of H star. So I can take the closure in B of H. So that is some subspace of B of H star, and I can take sigma of B of H with respect to that closure. Sorry, forget, no, just take that F closure. That F closure is a certain normed space. So I am saying that B of H can be identified with the dual space of that F closure. Right? That is something that one has to verify, but we will, I hope eventually I will convince you of this fact. Okay, but right now let me not get into the proof of this. I'll get back to this. Okay, and there is a theorem by Sakai which says that this pre-dual of a von Neumann algebra is in fact unique, meaning as a Banach space up to isometric isomorphism. If we have two Banach spaces M1, x1 and x2 such that M is identifiable with the dual space of these two, then M1 and M2 are isometrically isomorphic Banach spaces. That means the space of functionals that they give on M. So in general, if you take this M, so I am saying M lower star is unique. So this is Sakai's theorem. So what this tells you is that a von Neumann algebra, almost by definition, an abstract von Neumann algebra, comes with a God-given pre-dual. So that is unique. Okay. And there is this other theorem that you study in early Banach space theory, that any dual space is, if you take the unit ball of a dual space, it is compact in the so-called weak star topology. Okay, this is so-called Alia-Oglu's theorem. So I am just saying Alia-Oglu says that if I take the unit ball of M is compact in the sigma weak topology. So I'm using the same word to mean different things. So what I mean by the sigma weak topology is just sigma M. By this I mean sigma M star. Right, the topology on M that you get from M lower star. So I called earlier, So this is an abstract thing. There is, but there is said earlier about what this pre-dual of V of H is. But I'm saying that once you identify that pre-dual as a pre-dual, if you believe Sakai, then that thing is unique. So there's, no matter which way you came to it, there's only one thing it can be. Okay, so so let me say this thing that I forgot to say earlier. Namely, see, so von Neumann algebra, so summary, in summary, a von Neumann algebra has a God-given topology, a canonical topology, which is this weak star topology coming from the unique pre-dual. So it has this topology with respect to which its unit ball is compact. And whenever you have compactness anyway, then you have a good thing. That is the reason for many things that happen in the von Neumann algebra. And so it is important to look at, so I will use the word sigma weak topology for a general von Neumann algebra, for an abstract von Neumann algebra, to denote that topology coming from that pre-dual. Okay. Okay. Now the point is that if and once one has shown that what I called as F closure earlier is a pre-dual, that will tell you that this sigma weak topology, it will say that if M is a concrete von Neumann algebra, then it will say that the sigma weak topology and the weak operator topology, let me not say it. Let me say it on B of H. Agree on bounded subsets of B of H. That is the point I was making earlier, that F and F closure will induce the same topology, and so because F gave you exactly the weak operator topology and F closure gives you the sigma weak topology, which I haven't proved yet for you, then it will show that these two things are the same. And when you're dealing with von Neumann algebra, the natural things to look at are things which are continuous in this topology. The sigma weak topology is the natural object to look at when you have von Neumann algebra. And so let me just say that there is this just a minute. One thing in the last lecture, which it is because this sigma weak topology is a mess and a pain to work with in general, whereas the weak operator topology is something very tangible that you can lay hands on and work with. And because of this fact, it is good to be able to work on norm-bounded sets. And so there is the theorem of Kaplinski, which we will have to use on occasion, which says that if A is a is any unital star algebra inside B of H?
Y.
Huh?
Y. Kaplinski has Y.
Sorry. Then last time what we saw was that from the von Neumann density theorem, what we saw was that A is strongly dense in A double prime. Then, now Kaplinski says something stronger. He says that in fact, if I take the unit ball of A, if I take the closure of the strong operator topology, that is equal to the unit ball of A double prime. So you just think about for a minute. See, the von Neumann density theorem says that A is strongly dense in A double prime. So anything in A double prime can be approximated from A. But this says that if you take anything in the unit ball of A double prime, you can approximate by things in the unit ball of A. And because the topology, sigma weak topology and weak operator topology and everything is the same, and everything is metrizable, that earlier thing that I said, if I take all, see if I take an, why am I mumbling? The object of by saying something earlier about something being metrizable was to say that on a separable Hilbert space, if you take the weak operator topology on bounded subsets of B of H, the weak operator topology is metrizable. I'm being very haphazard in preparation. So let me say this again. So where was that statement that I made? I said that if you take sigma of XS or span S or span S closure, they are the same on bounded sets, right? So if I take S to be all operators of the form, okay, I might as well do this thing properly now. See, B of H, any operator on a Hilbert space, separable Hilbert space, so it has a countable orthonormal basis. So any operator can be represented by an infinite matrix, right? So, and not every infinite matrix will give you a bounded operator. You have to worry about which ones do and so on. I keep forgetting what I started to say. Huh? Exactly. So every operator gives rise to a matrix, and only some matrices give rise to operators. But if I take, for example, it's separable. If I think of it as L2, which means spelling out an orthonormal basis for H, then in here I can look at operators which are called Eij, which as matrices have 1 in the Ij spot and 0 elsewhere. Okay? So these are all operators on this, and it is easy to see that these Eijs finite linear combinations of these, not quite. No, only when I get to the closure, because I'm fixing the basis. So I'm sorry if I'm making a mess of this thing. So no, forget everything I said in the last 3 minutes. Let me start again. And what I had hoped to talk about today was I want to talk about B of H as a one-Neumann algebra. I want to talk about the pre-dual of B of H to get a feeling for that thing. And I also want to discuss two fundamental theorems in operator theory that one will use all the time, the so-called spectral theorem and the polar decomposition theorem. Okay. So, to get to first base with these notions, let me first discuss all this when H is finite dimensional. Let us understand what all these things are, and then we will see the passage will become a little more transparent, I hope. Okay, so let's start with the spectral theorem. So now H is finite dimensional, so I might as well assume that H is Cn. Once I fix an orthonormal basis, I assume that H is n-dimensional Hilbert space, so it is, I identify the iron orthonormal basis of H with the standard orthonormal basis for Cn. And by the same token, I identified B of H with MNC, M capital NC. Okay. So what does the spectral theorem say? It says that, so let X in B of H I said in terms of matrices, says that then following are equivalent. X is normal, that means X commutes with its adjoint. Two, X is diagonalizable. There exists U in UN, a unitary matrix, an n by n unitary matrix, such that U x U star is a diagonal matrix. I will just write alpha for the diagonal matrix with alpha 1, alpha n on the diagonal. Okay. Any matrix can be, any normal matrix can be conjugated by a unitary matrix to give you a diagonal matrix. That's what the spectral theorem says. This is actually something that Partho put up on his board here somewhere. Norm of any norm of any element of a commutative C-star algebra is equal to its spectral radius. And that's exactly what I've said. I would say take the spectrum, take the maximum. So that is the norm. Okay, so this is what the spectral theorem says. Okay, and what does the polar decomposition theorem say? Okay, so before I get to that, let me just say, already in I think yesterday's lecture of Partho, he's been trying to tell you the importance of the notion of functional calculus. You have some algebra of functions, and for operators, for some algebras of operators, you get a homomorphism from the function algebra to the algebra of operators, which you denote by f going to f of x. where if f is a polynomial, then that p of x is the natural polynomial. And when x is when you have a, so the first example, Partho talked about the analytic functional calculus or holomorphic. If you take any element of any Banach algebra, then you can get a mapping from the algebra of functions which are holomorphic in the neighborhood of the spectrum into the algebra, which you call the analytic functional calculus. If you have two elements of the algebra, then fg of x is equal to fx times g of x. What is good about C star algebras is that one has not just, see one is getting greedier and greedier. Initially you had a polynomial functional calculus, which any algebra will give you. And then through this contour integration, one got this holomorphic functional calculus in any Banach algebra. So you've expanded the scope from polynomials to holomorphic functions. Now you want to expand it even further, not only holomorphic, but even just continuous. So one wants to have a continuous functional calculus. So that is what one will prove in a C star algebra. In a C star algebra, if x is a normal element in a C star algebra, then you have a homomorphism from the continuous functions on the spectrum of x to the C star algebra, f going to f of x. And you can use the availability of lots of continuous functions to say sensible things about the C star algebra. Now in von Neumann algebras, it is you will go one step further. C star algebras are like continuous functions, C of x. Von Neumann algebras are like L infinity of x, just bounded measurable functions. I will make sense of the indicator function of an element, of a normal element, a function which is not continuous. Right? So the so-called measurable functional calculus is what von Neumann algebras will give you. That is what we will be doing. But before we get to all that, so let us see just here at this baby stage, you can see what the continuous functional calculus is for C star algebras in finite dimensions. What will f of x be? You will see that this is actually equal to u star diagonal f alpha. We call the diagonal alpha is the u. If you conjugate by u, the spectral theorem says you might as well assume that your self-adjoint is diagonal. So for diagonal things, I should tell you what the functional calculus is. And if I want to tell you what log of x is, and if x is a diagonal matrix, then log of that is going to be log alpha 1, log alpha n. For that to make sense, of course, all the alphas must be positive. So the functional calculus will make sense only where the functions are defined on the spectrum. Okay. So for example, one can talk about mod x. So notation, if x is for any x in Mn, x is not normal, so I can't apply functional calculus. But I can look at x star x, which is self-adjoint, and it is in fact positive. The function f of t equals square root of t is a continuous function defined on the positive line. So I can define this as this power half. That is something which will make sense. But here it says exactly that if mod x, if x star x has eigenvalues alpha 1, alpha n, mod x is the diagonal matrix with square root alpha is. Okay. So now let's get to the polar decomposition. If you take any x in Mn, this is again the finite dimensional version. I will later today, I hope, get to talk about the infinite dimensional version of the polar decomposition. This implies there exists a U in unitary such that x equals U mod x. So this you must compare with the polar decomposition of complex numbers. If z is a complex number, I can write z as e to the I theta times mod z. So this is what the polar decomposition says. Right? So notwithstanding all my mumbling in the first half an hour of my lecture, I hope at least the spectral theorem and polar decomposition in finite dimensions is clear. So now let me get to, so I want to understand what Mn of, I want to understand B of H star is, remember? So for finite dimensional H, let us see what this is. So that is, I want to see what Mn star is. I'll drop the C, I'll just write Mn. What is the pre-dual? In finite dimensions, if something is the dual space of some finite dimensional space, every finite dimensional Banach space is reflexive. So lower star and upper star, everything is the same. Okay. So as a vector space, you can identify it with Mn. The only thing that is not clear is what is the norm of this thing. I want to understand the norm of this pre-dual. Okay. And so here is let me give away the answer. Here the beautiful fact is you would have seen this in your first course in functional analysis. You would have seen that if you take the sequence space, C0, 1, right, for usually the sequences which are converging to 0, null convergent sequences with the supremum norm. So this is a subalgebra of L infinity. Okay. So what I am saying is that C0 star is actually L1, though this is something you have seen, and L1 star is L infinity. And the analogy to keep in mind is, take an infinite diagonal matrix with this as spread on the diagonal of a matrix everywhere else. When was give you a bounded operator? When it is in L. The general, we will see that there is this in B of H, there are the so-called finite rank operators. Operators finite rank. If you take, and they will be a subspace of B of H. Take the norm closure of this. This is usually called compact operators. And once understand the log of this is that k of h star is C1 of h and C1 of h star equal to B of h. So somehow the analog of L1 will be the pre-dual of P of h. And to see complete the finite rank operator, weak operator topology, you get all operators. So this is an exercise. And there is a certain other norm that I'll put on finite rank operators, which I'll call the one norm, will be this pre-dual. So they'll turn out to be a certain other norm on the closure of the finite ranks, which will turn out to be exactly the C1. Okay, to understand any of these norms really, the first thing one should really notice is that all these norms are really okay, so let us try to understand the norm of, let us try to understand Mn star, which is the same as Mn pre-dual, as a Banach space, right? So so what are the linear functionals on this? So as a vector space, you can think of Mn as just Cn squared, n squared dimensional space. And so its dual space is just also identified with n squared dimensional space. I can think of this as identified with Mn. And suppose I take, as an element of the pre-dual, I will use symbols like rho rather than, and elements of Mn I will denote as x, and elements of the pre-dual I will write with the symbol rho. So how is the duality given? So rho x. So the rho is also, one thinks of this as actually equal to Mn as a set. As a vector space, I must tell you what the norm is. So what is the action of rho on x? Your general duality in finite dimensional space, finite dimensional Hilbert space, will tell you that this looks like summation rho ij bar xij. Right? That's exactly what this is. Now, with a little arithmetic, you will see that this is nothing but the trace of rho star x. This is matrix multiplication. I take rho star is the complex conjugate matrix. If I take rho star, there is a matrix of ij and t rho ji bar, and then you take some, you verify this. So this is what this is how the pre-dual the dual acts on Mn. So now I want to find the norm. So what is the norm of such a rho? So I'll write the one norm for the norm of rho as an element of Mn lower star or Mn star or Mn. What is the linear functional norm of that rho? So to see that, so this by definition going to be the soup of absolute value trace of rho star x for norm x. There are many norms floating around, so let me write infinity denote the operator norm. So I want to find what the infinity norm is. See, there is parallel to this thing. I have the infinity norm here. I am trying to find out what the one norm is. Except we have matrices now, not sequences. Okay. So what is this? Okay. So I want to say that see the spectral theorem will tell you that rho can be written as U mod rho. I am polar decomposition, sorry. It will tell you can write this. So I can write, so if I want to look at this quantity, what I get is equal to trace of mod rho is self-adjoint. So there is just trace of mod rho U star x. Okay. So which is really see this trace is the pairing. The trace of rows. What I am trying desperately to say here is that in fact, see x and U star x have the same norm, operator norm, infinity norm. And so as a functional, if we look at mod rho acting on U star x, that will be bounded by norm of mod rho times norm of U star x, which is equal to norm of x. So finally what you will see is that norm rho 1 in fact I am saying will turn out to be nothing but trace of mod rho. I put up enough competence there for you to convince yourself that this is exactly what you will get. Because of the fact that norm of U star x infinity norm is the same as infinity norm of x. So if you multiply by unitary, you don't change the unit ball of the operator algebra. Right? So this is equal to the one norm of this what shall I call it, pi. If rho equal to mod rho is diagonal pi. See, that is what the trace is. The trace, so the trace of mod rho is really the trace of any self-adjoint operator is the sum of its eigenvalues. So if mod rho is diagonalized, is diagonal from pi's, then the trace of mod rho is just the sum of those pi's. So what we see is that the pre-dual of Mn is Mn with this one norm. And what I was trying to say earlier is that again I am leaving gaps, I am not writing the proof in full detail. What I am trying to say is that from this fact one will, in fact I want to say that B of H lower star is, okay, wait a minute. So let me just say that this is, so if I think of B of H as infinite matrices with induced bounded operators, I want to identify what its predual is. So if I have an element of the predual of B of H lower star, it acts on infinite matrices. So if I have a row in here, then so I can take an element X in here and look at only these corners. Only look at things which look like 0 up to stage n. I look at M and C sitting naturally inside B of H. Every linear functional on B of H will in particular restrict to such thing to give you a linear functional on Mn. And what will be the norm of that as a functional on Mn will be exactly the trace norm of that corner. And because, and it is easy to see that the matrix inducing the functional is unique in any Mn. So I'm saying, so starting with rho, for each n I will get an n by n matrix. And what I will find is that if I think of rho n as an element of Mn lower star, which is just obtained by restricting to the action on the corner there. So given an element of B of H lower star, I have a sequence of such functionals. And if I think of this as sitting inside Mn plus 1 lower star, because I identify these with just matrices after all. If I think of rho n as also sitting inside n plus 1 size matrix, then what you will see is that in fact rho n will be a corner of rho n plus 1. They will all be consistently defined. So this rho will give you a consistently defined sequence rho n of matrices, and the fact that the whole rho is a bounded linear functional will tell you that, and the fact that the norms of the rho n's is exactly the norm of rho restricted to that piece will tell you that in fact limit norm n m tending to infinity n smaller than m, rho n minus rho m 1 is 0. So this is a little work, but one can see that these things, the rho n's will be converging in this norm. So in some sense I am saying that B of H lower star is the completion of all possible, I should have said finite rank matrices. You take all finitely supported matrices, which all give bounded operators on B of H, and you give the norm given by the one norm. The completion of that is exactly B of H lower star.
Except that you thought of them as functionals, and so this norm would be for B of H upper star.
Huh?
So you used reflexivity somewhere in the finite dimensional case.
No. I'm saying that see each rho n will give you an element of that what I called F, what I called f before. And so I am saying that this rho n will converge to f, to rho as an element in B of H star.
B of H, which star? The lower star or upper star?
No, upper star. That I said earlier that B of H lower star is the closure in B of H upper star of the finite ranks. In fact, you don't have to take all finite ranks, it is enough to take only finite rank with respect to a specific basis. Finitely supported matrices, you take the completion with respect to that, and the norm is the one norm. Okay, so I hope this didn't confuse too much, but the point is that one has to be careful about taking traces. You can't take the trace of any matrix just because not every sequence is convergent, some is summable. You can't take a matrix and just sum all the diagonal entries and hope to get something which is independent of which basis you choose. And so this B of H, so what I'm saying is that B of H lower star. So I'll just say this as a fact. There exists a class which I'll call C1 of H, which is contained in B of H, in fact. In fact, these are contained in compact operators. With these good properties, that if you take any x in C1H, if you think of the matrix, so I am just saying that for all x in this and rho in this and x in B of H, the pairing. See, I am saying that this is the dual space of this. That means I will have a pairing. Given something here and something there, I will get a number out of it. Right? So I am saying B of H is the dual space of rho. So if you want the pairing like this, or x of rho or whatever, is nothing but trace of rho x. No, that is because earlier I had to put the star because I used the Hilbert-Best language to write the inner products. So the point is that the adjunction is also a norm-preserving thing. So as far as the norm is concerned, it doesn't make a difference. So what I'm saying here is that this makes sense. So this is, in fact, this has many things are being implicitly stated here. It says that this is actually an ideal, meaning if I take something here and something here and if I multiply, the answer will be here. This is an ideal of this algebra, and for everything in this class, I can make sense of the trace. So what does that mean? If I take any orthonormal basis and represent that operator with respect to that basis, then the diagonal entries will be summable, and the sum of the diagonal entries will give you an answer which is independent of the basis that you choose. See, all this requires some verification, and I don't want to get into detail, but you can see all of this in, for example, the Satila Shizu thing. He'll tell you why these things are true. Okay, so maybe I should get on with. I never got to spectral theorem, did I? No, I'm being very. I think it's better to be slow rather than do too much. So let me cover a few comments that I've made in the notes. Okay, so going back to the thing, the point of the last half an hour's rambling was to show that B of H is indeed a dual space, and to give you an idea of what the pre-dual of B of H looked like. I haven't said anything about the uniqueness, why it is unique and so on, but nor do I intend to. Okay, so in the category of one-Neumann algebras. Okay, see, if you're talking about C-star algebras, if you're talking about the category of C-star algebra, in the language of C-star algebra, the natural thing would be, the objects will be C-star algebra. These are involutive algebras. And what are the morphisms? The maps between these objects will be their algebras, so you would like them to be algebra homomorphisms, and you would like them to be star homomorphisms. And further, ideally you would like them to, because these things come with a norm, you would like these homomorphisms to be bounded. It is a theorem that Partho will, I assume, show for you sometime, that any homomorphism of C-star algebras is automatically bounded. He showed you this fact using the spectrum is always, they have spectral inclusion, and the norm is determined by spectral radius and the C-star identity. So anyway, so in C-star algebras, the natural morphisms in the category of C-star algebras are just star homomorphisms. When you talk about one-Neumann algebras, at least at the abstract level, what are the morphisms? So given two one-Neumann algebras, M1 and M2, the morphisms would mean star homomorphisms, which are these two. The key feature of one-Neumann algebras is in addition to the star algebra structure, that pre-dual that they have, the sigma weak topology that they have. So there is the sigma weak topology on domain and range, which are continuous with respect to sigma weak topologies. On domain and range. So rather than writing all these things again and again, so one will just abbreviate all these things to say, one will use the word normal. A map of one-Neumann algebras will be called normal if it is continuous with the correct topologies. So the natural morphisms are the normal star homomorphisms. Okay. So again, there's a fairly, I mean, not difficult fact, but one has to do a little bit of point set topology, Banach space theory sort of thing, which is the following. So if you have, in C-star algebras, you know that if A is a C-star algebra and if A naught is a sub star algebra which is norm closed, then it is itself a C-star algebra, naturally. So I want to talk about one-Neumann subalgebras. So if you have M, okay, so let me say the following thing. So M concrete one-Neumann algebras are abstract one-Neumann algebras. This is the easy part of the theorem that one wants to prove. So I talked about concrete and abstract, but I want to say that any concrete one-Neumann algebra, that means a sigma weakly closed. In fact, more generally, I would say, more generally, if n is a sigma weakly closed star subalgebra of a one-Neumann algebra M, so all this is abstract, right? No, abstract. Then n is also an abstract one-Neumann algebra. That means I just have to produce that pre-dual because it is a seesaw algebra. So the details are listed in that in that remark in here, which I will skip now. In remark 2.2, I do 2.23 or something. One says that any such one-Neumann subalgebra of a one-Neumann subalgebra, one-Neumann algebra is a one-Neumann algebra. So in particular, whatever are concrete one-Neumann algebras, by definition, if I use the word one-Neumann subalgebra to mean a sigma weakly closed star subalgebra of a one-Neumann algebra, then a concrete one-Neumann algebra is nothing but an abstract one-Neumann subalgebra of Beer-Weiss. And so by what one is shown here. Okay, so so this is where that let me illustrate the Kaplinski's theorem. So I want to say that suppose I take so let me prove this fact using Kaplinski. Suppose M is a concrete one-Neumann algebra. So it is sitting in set B of H. So it is WOT closed in B of H. So in view of the remark that I have made here, it is enough for me to prove that M is actually sigma weakly closed in B of H. Okay, then it will also be an abstract one-Neumann algebra. I'm trying to prove that if I have a concrete one-Neumann algebra which I call M, I want to say that it is an abstract one-Neumann algebra. So what does this mean? This means that it is a WOT closed star subalgebra of B of H. But what one has just said over there in that remark is that if you take a sigma weakly closed subalgebra of an abstract one-Neumann algebra, that is an abstract one-Neumann algebra. So I just need to verify that this implies sigma weakly closed. In B of H, right? As a subalgebra of B of H, if I know that it is sigma weakly closed, then it will follow that this thing is indeed true. So sorry for belaboring a trivial point, but it is good to see an instance of how and where you will need something like the Kaplinski density theorem. Okay, so suppose X alpha in M converges to X, or no, X is in M sigma weak closure. Then I want to say that X belongs to M. Without loss of generality, norm X is less than or equal to 1. Okay. Okay. Then what I know is that how do we maybe I should so see what Kaplinski will tell you is, see X is in if I take A as equal to M, what Kaplinski will tell you is that X is in A double prime in A closure weak operator topology. Okay, I'm making a mess of it again. So, see the point is this: on the unit ball, the sigma weak and weak topologies are the same. And if you can approximate something in M closure by the sigma weak topology, then you can approximate it the sigma weak topology by things in the unit ball. If something in the unit ball is approximable by something in the algebra, you can approximate by things in the unit ball of the algebra. That is what Kaplinski says. But if X is the limit of X alpha, so that is the idea, X is limit X alpha with norm X alpha less than or equal to 1. Limit meaning it's sigma weak. But on bounded set, by the X alphas, so unfortunately it is the nature that you have to get into these topological skirmishes periodically to get what you want.
You can use that your fast lemma that insta is exactly equal to that and the closure of that odd semi-norm or WT semi-norm.
Okay.
And then the unit ball the same. Something is if you take from M bar closure with respect to sigma v. Today's fast and that sigma is the closure of this all those things. And that is the F bar. The unit ball of one is the same.
So that is exactly what I want to get down to.
Yeah.
But to get down to a priori, I needed Kaplinski to say that you could choose approximates from the unit ball. That all the action was happening in a bounded region, and there the two topologies were the same, and so you have actually weak convergence. Okay, I haven't even got down to so the spectral theorem. I think one should Yeah, I think maybe I should forget the last lecture and then try and do cover the first 5 lectures or as much of that as I can. So I still haven't got down to spectral theorem or polar decomposition in infinite dimension, but that we'll try and quickly run through next time. Okay, you may go if you want. I'll take a while getting all my things together from here.